All right, so computers that learn. It's not science fiction anymore, is it? We're diving deep into machine learning today with, you guessed it, Tom Mitchell's book, The One and Only Machine Learning.
A true classic. And it really has changed the game. I mean, it's not just about computers anymore, it's about understanding intelligence itself. And Mitchell, he takes us there step by step.
From the ground up, which is awesome. And he doesn't waste any time. He jumps right in with designing a learning system using, of all things, checkers.
Such a great example, though, right? Because it highlights these key decisions you face no matter what kind of learning system you're building. Like, first off, what's the training experience going to be? Are we treating our AI like a chess prodigy, giving it the rule book, the grandmaster strategies? Or are we letting it loose in the park to play against anyone and everyone?
Learning from experience, trial and error.
Precisely. And both have their merits. Direct feedback, like here's the optimal move, it's fast. But that indirect feedback, figuring things out from wins and losses, that can lead to some really deep intuitive learning.
More nuanced, for sure. And that actually leads perfectly into Mitchell's concept of a target function, which sounds way more complicated than it is. At least I hope it is.
Oh, it's simpler than you think. Really, it's just about defining what you want the system to actually learn. So back to our checkers board. Are we aiming for a program that simply picks the best move right now based on the current state of the game? Or do we want it to evaluate strategically how strong any board position is regardless of the next move?
Because those are two different skill levels,
Right.
like calculating versus strategizing.
Exactly. And that takes us to another crucial point: representation. How do we represent the information the system needs to learn? So with the checkers board, we might use something called a weighted linear function. It analyzes features like how many pieces each player has, where they are, and spits out a score of how strong that overall board position is.
Okay, so far so good, I think. Then Mitchell gets into concept learning. Like teaching a computer to recognize a perfect day for being outside based on stuff like temperature, wind, humidity. And honestly, why isn't my phone doing this already?
The future is coming. But yeah, it illustrates beautifully how a learning algorithm works. It tests hypotheses, right? Starts broad, maybe, okay, above 70 degrees is a good starting point for a perfect day. Then it gets more data, sees some perfect days are cooler, some warmer, and it refines that definition.
So it's like us. We generalize, then we encounter exceptions, and we're like, okay, unless it's humid.
Exactly. Generalizing, specializing, constantly refining. But of course, there's a catch. And Mitchell, he calls it overfitting.
Which is where the computer throws a tantrum because the real world doesn't fit neatly into its little training data box.
In essence, yes. Overfitting is when the algorithm gets too obsessed with the examples it's seen and forgets how to generalize. It's like acing a test by memorizing the answers but not actually understanding the material.
Been there. So how do we prevent our learning algorithms from becoming glorified memorization machines?
One way is decision tree learning, literally a tree-like process of making decisions. Back to the perfect day example, the tree might ask, is it raining? If yes, okay, no playing outside. If no, then maybe it branches off to, is it above 75 degrees, and so on.
Breaking it down, which makes sense. But couldn't that get out of hand? Too many branches, too many exceptions?
Absolutely. Overthinking is a thing, even for algorithms. Decision trees can get way too specific, too complex. That's where we prune them back, simplify, make sure they're focusing on the important stuff.
Less is more.
Often, yes. A simpler tree is easier to understand, less likely to get tripped up by weird data points. It's about balance.
Balance. Got it. And speaking of mind-blowing, we haven't even touched on neural networks, which, let's be honest, are everywhere these days.
For good reason, they're powerful. Think of it as a network, kind of like our brains, with interconnected nodes. Each node processes information, and the connections between them, they have these weights that determine how signals flow through the whole system.
And as the network learns, it's like those connections get stronger or weaker based on experience.
That's the basic idea, yeah. Of course, it gets way more complex than that, but you've got the right concept. And one of the key algorithms here is backpropagation. Basically, the network learns from its mistakes. Like you touch a hot stove, you get feedback, you adjust your behavior accordingly.
Painful, but effective.
hmm
So the network makes a prediction, sees how wrong it was, and then tweaks those connections to do better next time.
Exactly. And it does this over and over until it gets really good at making those predictions. Mitchell even walks us through a simple game like tic-tac-toe to show how it works. The network sees different board positions, the outcome, win, lose, or draw, and it uses that to learn which positions are strong or weak. Eventually, it becomes unbeatable.
No more challenging computers to tic-tac-toe then. I'll add it to the list. But how do we know for sure that it's actually learning and not just getting lucky with its guesses?
Ah, the million-dollar question. That's where we dive into evaluation, my friend.
No more letting the computer win just because it's easier that way.
Tempting, but no. We need rigorous ways to see how our model performs on data it's never seen before. We've got to make sure our AI is as smart as we think it is.
No pressure. All right, so we've covered designing these learning systems, how they actually learn, how we make sure they're learning. Anything else before we jump into the really complex stuff?
Well, Mitchell doesn't just throw us into the deep end, right? He knows how to pace himself. So we move on to something called Bayesian learning, which sounds a lot more intimidating than it actually is.
Oh, wait, Bayesian learning. Is that where we finally get those self-aware robots we were promised?
Not quite, but it does involve giving our machines a little bit of a head start. Imagine, instead of making them learn everything from scratch, we could inject some pre-existing knowledge.
Like a cheat code for intelligence.
Kind of. It's more like giving them a nudge in the right direction. Say we're teaching a computer to recognize cats. We can tell it up front. Hey, cats usually have 4 legs, pointy ears, a tail, just a heads up.
So we're saving it from having to analyze thousands of cat photos to figure that out. Smart.
Exactly. We're basically encoding our prior beliefs into something called a prior probability distribution. Think of it as a starting point for the algorithm's learning journey.
So it's not just about blindly crunching data anymore.
Not at all. We're combining data with what we already know using a lovely bit of math called Bayes' theorem, and out pops a posterior probability distribution. Basically, our updated beliefs after considering both the data and our prior knowledge.
So it's like starting with a hunch, looking at the evidence, and forming a more informed opinion.
Spot on. And this posterior, it becomes our guide. It helps us make decisions. And that's where the Bayes optimal classifier comes in.
Optimal. I like the sound of that.
Right. In theory, it's the best possible way to make a decision with the information you have. It considers all possible hypotheses, weighs them based on their probability, and picks the most likely winner.
Sounds exhausting, to be honest.
It can be. In practice, calculating this optimal classifier, it can be computationally very, very expensive.
So great in theory, not always practical in the real world.
Sadly, that's often the case. But even if we can't perfectly calculate it, we can approximate it. And the principles behind Bayesian learning, they've given us some really cool tools like Bayesian networks.
Oh, aren't those diagrams with circles and arrows and I'm getting a headache just thinking about it.
They do look a bit intimidating, but they're actually pretty intuitive once you get the hang of them. Imagine you're mapping out all the things that might make you late for work traffic, weather, how much sleep you
The
got.
possibilities are endless.
Right. So Bayesian networks, they let us visualize all these relationships. Each circle is a variable, each arrow is a connection, and we can actually calculate the probability of being late based on any combination of those factors.
Like a flow chart of potential disaster.
In a way, yes.
Right.
But they're incredibly useful. Medical diagnoses, spam filtering, you name it.
Okay, I'm starting to see the appeal. So we build these networks, we feed them data, and then what? How do we actually put them to use?
They become knowledge repositories. Think of them like superpowered textbooks. Let's say we have a Bayesian network trained on medical data. You input a set of symptoms, and it can tell you the probability of a patient having a particular disease.
A personalized, probability-driven medical diagnosis. That's both impressive and slightly terrifying.
Right, and that's just one example. They're used in finance, risk assessment, all sorts of fields, but I can see your brain starting to smoke, so let's give it a bit of a break. Mitchell, thankfully, changes gears a bit and introduces us to the minimum description length principle, or MDL for short.
MDL. Does it involve spa treatments for overworked algorithms?
Not quite, but I like the way you think. It's more about finding elegance in simplicity. The MDL principle basically says that the simplest explanation is often the best one.
Less is more. Again.
Exactly. And it ties into information theory. How do we transmit information efficiently? The most concise explanation is often the most powerful.
So it's not just about finding any explanation, it's about finding the most elegant and efficient one.
Precisely. Every bit of information should have a purpose. And this becomes crucial as we start talking about the limits of learning itself, which is where computational learning theory comes in.
Okay, things are getting serious now. Are we about to unlock the secrets of the universe?
Maybe. But first, we need to understand what's even learnable. Computational learning theory helps us analyze how complex a learning problem is and whether or not it's even possible to solve it, even with infinite data.
So are there some things machines just can't learn no matter how hard we try?
That's the million-dollar question. And this theory tries to give us an answer. One of the key concepts here is the probably approximately correct learning framework, or PAC for short.
Probably approximately correct. That
I'm-
doesn't exactly inspire confidence.
I know, right? But it's actually a very pragmatic approach. It acknowledges that in the real world, we rarely achieve perfect accuracy. We aim for models that are probably right most of the time.
So we're embracing the uncertainty and aiming for good enough.
Exactly. And PAC learning helps us figure out how much data we need to be probably approximately correct with a certain level of confidence.
So more complex problems, more data.
Makes sense, right. And remember that MDL principle. Simpler hypotheses require less data to learn. So simplicity really is key.
Elegance and efficiency, all in one package. I'm starting to think the MDL principle should apply to life in general.
I'm with you on that. But even with elegant and efficient models, we still bump into limits. And that's where something called the VC dimension comes in. Imagine you're trying to separate data points into different categories, right? The VC dimension tells us how complex our decision boundary needs to be to perfectly separate those points.
Okay, so if I'm sorting apples and oranges, a simple line might do the trick. But if I'm trying to separate different types of apples based on subtle color variations, I'll need a more complex boundary.
Exactly. And the more complex the boundary, the more data we need to learn it effectively. And here's the kicker. If the VC dimension is infinite, if our hypothesis space is infinitely flexible, then we might never learn an accurate model, even with all the data in the world.
So even with all our fancy algorithms and mountains of data, there are still limits to what we can know. Humbling, to say the least. But hey, nobody said machine learning was going to be easy.
Exactly. And Mitchell, he doesn't let us forget that. He then shifts gears and introduces us to instance-based learning.
Instance-based learning. Lay it on me.
It's refreshingly straightforward, actually. Instead of building a complex model up front, we just store all the training examples. Then, when we encounter a new instance, we find the most similar examples we have seen before and use those to make a prediction.
So it's like judging a book by its cover. Or judging a book by comparing its cover to other book covers you've seen.
You got it. The most famous instance-based learning algorithm is called K-nearest neighbors, or KNN.
Oh yeah, KNN. I think I've heard of that one. It finds the K most similar examples, right? Like if I want to know what kind of music you like, I'd look at your 5 closest friends and see what they're listening to.
Exactly. It's very intuitive. But, like all things, it has its downsides. It can be slow, especially with a lot of data. And it struggles with something called the curse of dimensionality. Basically, as the number of features or dimensions in our data increases, it gets harder to figure out what similar actually means.
So too much information can be a bad thing. Who knew?
It's true, but even with its quirks, KNN is a useful tool. And Mitchell, always the overachiever, he throws another paradigm at us. Genetic algorithms.
Genetic algorithms. Are we talking about algorithms that can evolve like living organisms?
We're closer than you think. Genetic algorithms, they take inspiration from natural selection. Imagine you have a bunch of candidate solutions, each one like a digital organism with its own set of genes.
I'm picturing a bunch of algorithms in tiny lab coats battling it out for survival.
It's a good visual. So we test how well each solution performs. The better ones get to reproduce by combining their genes to create offspring solutions.
And just like that, we have algorithms breeding and evolving. This is getting out of hand.
But in a good way. And of course, there are mutations, random changes to keep things interesting and help the algorithm explore new possibilities.
So survival of the fittest, but for code. This is blowing my mind. But how do we actually use these genetic algorithms in machine learning?
Oh, they're incredibly versatile. Optimizing neural networks, finding the best features for a problem, even designing entirely new algorithms. We're essentially using evolution to improve our AI.
I'm both amazed and slightly terrified at the same time. But I have a feeling it's about to get even wilder, right? Because Mitchell doesn't just stop at genetic algorithms. He takes us to genetic programming.
We're going full meta. Genetic programming, it's not just evolving parameters or solutions, it's evolving actual computer programs. Code that writes itself, improving with each generation.
Hold on, the programs are writing themselves. Is anyone else concerned about where this is going?
It's definitely a trip. But remember, we're still the ones setting the goals and the fitness criteria. These programs aren't gaining sentience or anything.
That's good to know. So what's the upside of all this code writing code?
Sometimes these genetic programs stumble upon solutions that human programmers would never have even considered.
So we've created something smarter than us, even if it's by accident. Got it. What could possibly go wrong?
You're starting to sound like a broken record. But you're right, it does raise some interesting questions. Anyway, shall we move on? Because Mitchell, he's got more tricks up his sleeve. He then takes us into the world of analytical learning. Remember how we talked about Bayesian learning, using prior knowledge?
Giving our algorithms a head start.
Well, analytical learning, it takes that idea even further. It's about using logic and reasoning, not just data, to improve our learning.
So less pattern recognition, more actual understanding.
Exactly. And one of the coolest examples of this is explanation-based learning, or EBL. Instead of just memorizing examples, EBL tries to understand why an instance belongs to a certain category.
Okay, I'm listening. Give me an example.
Let's say we're teaching a system to tell the difference between, I don't know, cups and bowls. With EBL, we give it some background info, like cups are for drinking, they often have handles, that kind of thing.
We're giving it a crash course in kitchenware 101.
Exactly. So when we show it a cup, it can analyze its features, the handle, the size, and explain why it's a cup, not just because it looks like other cups it's seen.
So it's actually using knowledge to reason. That's next level stuff.
It is. But of course there are challenges. Like, how do we provide all that background knowledge, especially for complex domains? It's one thing to explain cups and bowls, but what about, say, the stock market or international politics?
Yeah, my brain's already full.
Mine too. And that's where things get even more interesting because Mitchell dives into these hybrid approaches, combining inductive learning, learning from data, with analytical learning, learning from knowledge. It's like we're building a more well-rounded AI.
Okay, I'm all for well-rounded AI. What do these hybrid approaches look like?
So one example is the knowledge-based artificial neural network, or K-BAN. Remember our neural networks with the nodes and the weights?
Like it was 5 minutes ago. Yeah, those things.
Right. So with K-BAN, we don't just build a random network. We actually structure it initially to reflect some of that prior knowledge.
So instead of a blank slate, we're giving it a head start.
Precisely. And then we use backpropagation to refine that initial structure based on the data it sees.
So it's learning, but with a little guidance counselor whispering in its ear.
Exactly. It's a really elegant way to combine those two approaches. But then what if our knowledge is even messier, more nuanced than we can easily encode into the network structure?
There's always a but, isn't there?
There's always more to explore. So Mitchell introduces us to tangent prop. Instead of directly encoding the knowledge, tangent prop uses these things called training derivatives.
Derivatives, as in calculus.
Don't worry, you don't need to dust off your textbooks. Basically, these training derivatives guide the network, telling it how its output should change when the input changes. But this guidance, it's based on our knowledge.
So we're giving it hints.
Exactly. We're saying, hey, if you see this in the input, it should generally lead to this kind of change in the output. And tangent prop, it tries to learn from the data while respecting those hints.
A balancing act between data and knowledge.
You got it. And, it makes you think, where does all this knowledge come from in the first place?
Right. Are we just supposed to magically beam it into these machines?
I wish it were that easy. Knowledge acquisition, that's a whole other fascinating field. Sometimes it's from experts, sometimes it's from textbooks, sometimes it's even from other machine learning models.
So it's like this ever-growing web of knowledge.
Exactly. And as we build more and more sophisticated AI, that interplay between data, knowledge, and learning, it just gets more and more important. And Mitchell, he does such a great job of driving that point home throughout the book. Building truly intelligent systems, it's not just about algorithms, it's about understanding how we learn, how we reason, how we see the world.
He's given us a lot to think about.
Yeah.
And honestly, I feel like I've only scratched the surface of this book.
Oh, absolutely. There's so much more to explore. But if nothing else, I hope it sparks some curiosity in our listeners.
That's what we're here for, right? To dive deep, to learn, and maybe have a few laughs along the way.
Exactly. And maybe, just maybe, inspire the next generation of AI enthusiasts.
Here, here. All right, folks, that's a wrap on this deep dive into machine learning. Until next time.